Dear students, welcome to a video in which I explain the principles of a non-linear least square optimization technique, and we will focus on the simplest example, which is the Gauss-Newton method. After watching this video, you should have a good understanding how this optimization technique works, why it does come with some caveats and should always be applied with care, but most importantly, you should understand why those optimization techniques are important in the geo and environmental sciences. So in a very abstract way, what we are talking about here are forward models. And those forward models, they encapsulate some sort of physical process. And the implementation of this forward model comes in very different shapes and very different ways. However, all those models have in common that they require a set of model parameters. And if those model parameters are well constrained, then the predictions of those models are meaningful. However, in practice, the model parameters are often not very well constrained, and this is why we need observations. So the idea of those optimization techniques is that we couple the observations with the forward models in order to constrain the poorly understood model parameters. And once the model parameters are constrained, then the predictions will be more meaningful. And we will call the way from left to right the forward modeling way. And if we go from right to left, we'll call this the inverse way. And typically the inverse way is harder than the forward way. So let's look at some examples. Shown here are students who carry out a geoelectrical survey. Geoelectrics is a specific geophysical technique that seeks to characterize the subsurface as a function of its electrical resistivity, and this resistivity is in turn a diagnostic of different subsurface materials. So the way this is done is that you induce a DC electrical current, and here you do this via electrodes attached to these wooden poles, and you also measure the corresponding potential drop at the surface, and by relating the potential drop to the induced current, you can derive a quantity that you call apparent resistivity, and this apparent resistivity is again a function of all the resistivities in the subsurface. So let's look at a simplified case. Everything is nicely horizontally stratified, and we have 4 different units: a topsoil, an unsaturated zone, a fully saturated aquifer that sits on top of some sort of bedrock materials. And all those units have different thicknesses and different electrical resistivities. And the way we probe this is by injecting the electrical current at the surface. And as we increase the distance of the current electrodes, we increase the depth of penetration, and we can probe deeper and deeper and deeper. So this is a crash course in geoelectrics, and in fact the physics are more complicated than that. For example, the flow lines are refracted at interfaces and so on and so on. But for now, you only need to know this problem is solved. It can be encoded in a numerical forward model, and this forward model needs some model parameters. And in this particular case, those parameters are the electrical resistivities and the thicknesses of the different layers. If you know those, you can predict what the measured apparent resistivity will be at the surface. And this is shown here. So on the left, we see the model parameters, so different layers with different thicknesses and different electrical resistivities. And our forward model can then predict what the corresponding observations will be of the geoelectrical survey. And so this forward way is interesting, for example, for survey planning. If you have some idea about the geological context that you encounter, you can use this to plan your geophysical survey. However, more interesting is the inverse way, meaning we have a set of observation, and what we want to know is what model parameters go along with those observations, because this is the goal of a geophysical survey. Let's look at a completely different example. What you see here are the famous rock cliffs which you will find in the Lauterbrunnen Valley located in Switzerland. However, while those cliffs are certainly a point of attraction for many tourists and parachuters, they are also quite dangerous because rockfall frequently occurs. The student that you see here sitting in the foreground seeks to quantify the frequency and the magnitude of individual rockfall events using a laser scanner. The physics of Rockfall can also be encapsulated in a forward model, and here we do this in an analytical way using a power law. This is simpler than the computer code that we needed in the example of geoelectrics. However, we also need model parameters, here V0, and the critical exponent C to make adequate predictions. So here I take a random guess for those model parameters, and I get a qualitatively okay descriptions. So what we see are small rockfall events which occur frequently, but we also see larger events which fortunately occur less frequent. However, are my model parameters good? Well, this is why I need to confront this prediction with observations, and I find there is a systematic misfit. And what needs to be done next is that we use the observations to constrain the model parameters so that we can make better predictions for especially the very large events. And now I will teach you how this is done. What follows next are a number of technical steps. And I don't believe that you have to remember all of this in its excruciating detail. However, what you should realize is that although some of the equations will become comparatively long and nested, this is not a difficult process per se. It's rather a process where we apply the same mathematical operations such as summations or derivatives again and again and again. We start by quantifying the misfit of our model prediction for a given model parameter vector and the observations, and we do this by calculating the squared residual between individual observation and individual prediction, and then we sum over all of the observations that we have. We call this function the cost function, and we would like this function to be as small as possible, because if s is small, then the misfit between model and observations is small, and that is what we're after. So we turned this problem into a minimization problem, and in any kind of minimization problem you need to calculate the derivatives, because at any given minima the local slope needs to be 0, and because we have multiple model parameters this needs to be the case for multiple equations. Okay, so we can take this one step further without including any specifics of our forward model G, and we do that by applying the chain rule. So the chain rule states that the derivative of something squared is 2 times the something times the derivative of the something. So I have done this here for you. The factor 2 nicely cancels out with this 1/2, and then the derivative of the residual is essentially the derivative of the forward model itself. So in order to go further, we now need to know which forward model are we talking about, and we will continue with the power law example. So in this example we have 2 model parameters, so we are left with 2 equations, one with respect to V0 and one with respect to the critical exponent C. And because we have an analytical representation of our forward model, I can do these derivatives analytically. It's comparatively easy for V0. Okay, the derivative with respect to V0 just cancels the V0. It's slightly more complicated for the derivative with respect to C, but nevertheless it can be done. Okay, so now we have 2 equations, and we need to find a combination of V0 and C which makes both of these equations 0. And because our forward model is nonlinear, there is no analytical solution to this, and we need to use numerical methods to find the zeros. Okay, and in the following I will sketch out how this can work in principle. And we will focus on the one-dimensional case first. So meaning that let's assume that for some reason we know what V0 is, then the only thing that we are left with is to find a C which would make this equation 0. And I call this function now f of c, just to make it slightly simpler. I don't know what type of function that really is, but it may look something like this. Okay, it's a nonlinear function, so it may have multiple zeros. And the question is now, how do I find those zeros? Okay, which c will end up being a 0? And because I don't know, I just take an initial guess, c1. And I evaluate the function at this initial guess c1, but unless I'm extremely lucky, the function f of c1 will not be 0 for that initial guess. So what to do next? The idea is that we now calculate the local slope around this initial guess. And this will essentially tell us where is up and where is down in this function landscape of f of c. Okay, so we calculate the Taylor approximation, which is a linear representation of this function around our initial guess c1. And this linear representation can be calculated comparatively easily. You just need another derivative, but you can do it. And once we have this linear approximation, I can immediately calculate the zero of this function. And the hope is that this zero of our local linear approximation is closer to the true zero than we were before. And it will be closer because we have calculated the local slope, so we kind of know where to walk. So now I'm at c2. I evaluate the function at f of c2. It's still not very zero, not close to zero, so I calculate local slope, but I will approximate the zero, okay? So this is c3, c4, and now there's already essentially no difference between c4 and c5. So we have reached convergence after 5 iterations. And this is the principle how you can find zeros using numerical methods. Using these kind of simple representation, you immediately realize if I had started with a different initial guess, I may have found a different zero, okay? And this is the root of the problem, that in nonlinear inverse problems you may have multiple solutions, and that's just something we need to be aware of. It's not something that we can get rid of. Okay, so this is the idea how we would do it in a one-dimensional case. However, we have 2 dimensions, but before we come to this, I'll present you the iteration scheme of the Newton method in a one-dimensional way, and this is essentially rearranging the terms of the Taylor expansion shown previously, and this is a straight, you could implement this straightforwardly even with comparatively little programming skills. Okay, problem is you need to know the derivatives. Okay, and we don't always do that, but in the case of our analytical forward model, we do. Okay. Next problem is how do we do this in several dimensions? Okay, so the way you can imagine this is if we have 2 parameters, V naught and C, then we don't only have a curve, we rather have a parameter landscape, and this landscape has valleys and hills, and the key is to find obviously the deepest valley in that cost function world. Okay, so here we are. Those are now 2 equations, and the idea is that we generalize this. Okay, it could also be NP equations. We apply the same principle as the Newton method, but in multiple dimensions. Okay, so I'll show you how to do this for one of those equations, and I take the jth one. Okay, so equation J will be the derivative of our forward model with respect to the jth model parameter, okay? And now I apply a linear approximation, but in a multidimensional way. So this is the constant term, and here is the slope. So you can associate those terms with what we've just seen previously. So this is the constant. So this is just a number because we evaluate all the derivatives at our initial guess. And over here we have the local slope of the function, which is now represented with the gradient. That gradient contains all the derivatives with respect to all the model parameters. Okay? And this should be a linear function of the model parameters, which it obviously is because we only take the first terms of the Taylor approximation. Okay, this looks slightly more complicated, and just to show you what's inside this gradient, the gradient contains all the derivatives with respect to all the model parameters. Okay, so I can write this out. First term, nothing changes, but in the second term, we now replace the scalar product between the gradient and the model parameter vector, and this uses the summation now over the number of model parameters. Yeah? So there's 2 summations, over the number of observations and one summation over the number of model parameters. Okay? And the next thing we could do is that we drag this derivative, d over dmk, into the brackets, and there will be then multiple derivatives, and it gets slightly more complicated, and then we need to do this for each of the equations, and we have np of those equations. Okay, so that is a bit complicated and nested, but not difficult per se. It's just the same thing applied again and again and again. However, there's a very neat way how you can simplify that drastically, and you do that by introducing what is called the Jacobi matrix. So the Jacobi matrix is a matrix, surprise, surprise, and it contains the derivatives with respect to all the model parameters in the rows, and we evaluate the derivatives at the respective independent variable in the columns. Okay, and this is just a definition, but it makes our life much, much simpler, because you can now use the matrix product between the Jacobi matrix and the residual between model prediction and observations. So you can represent, for example, this first constant term, which contains the summation over all of the observation. But remember, we have np of those equations, and so I can represent all of this in the matrix product between the Jacobi matrix and the residual vector. Okay, and you should take some time to realize that this is the case. And then we can go to this term over here, and that term is more complicated because it contains both products of first derivatives with respect to different model parameters and second derivatives. And here we approximate this. So this is an approximation, and we just take the products of the first derivatives and we forget about the second derivatives, okay? And we hope for the best. There are other methods which include the second derivatives, the so-called Hessian matrix, but the Gauss-Newton method doesn't do that, and it still works, okay? But here you should know that this is an approximation, okay? But what you should appreciate is that now our entire minimization problem, which contains NP equations, and all of those equations contain summations with respect to the observations and the number of model parameters. All of this can be written in a nice, simple looking equation using the Jacobi matrix and the vector, which contains all the residuals between observations and predictions. Okay? And now I kind of do the same rearrangement of terms as I did in the Newton method, so that I come to an iteration rule which tells me what is the minima of the cost function, because this is the goal of this whole exercise. Okay, and for this I isolate the difference between m and our initial guess m0. Okay, so this would be correspond to the C1s and so on that we had in the one-dimensional case. And now this involves that I take the inverse of a matrix, and this inverse here is at least defined because the product of the transpose with itself is a square matrix. So that works. May not always exist, but in many cases it will work. Okay, and this brings us essentially to the end. Okay, so here is our multi-dimensional expansion of the Newton method. So this method allows us to find zeros of system of equations, and this is the iteration rule. So you can start with some kind of initial guess, and this initial guess will be corrected as a function of the local slope in the parameter space. Okay, and then you get a better initial guess and you start the whole thing again. Okay, if this is the first time you see all of this, you may take some time to digest this. But I can let you know, you can code this kind of algorithm with comparatively rudimentary programming skills. Okay? And you have to remember, we need a good initial guess. It should include some reasonable prior knowledge, because otherwise we may find another minimum, which is, however, not not the global minimum, okay? And there's a problem here. We have to know the derivatives, okay? And how do we know the derivatives if our forward model doesn't have an analytical representation? How do we know the derivatives, for example, for the forward model that was relevant for our geoelectric survey, okay? So this is a much more complicated model, and I couldn't calculate the derivatives straightforwardly analytically, okay? However, also in this case, you can do it numerically. It means you essentially have to wiggle a little bit on the local parameter close around your initial guess, and this will give you an approximation of the local slope in the same way as the analytical derivatives. It does require more computation, more function evaluations, and so on, but it is possible, okay? And if you have a numerical forward model, but also an analytical one, you can use many pre-built packages which exist in virtually all programming languages, and they exist in all programming languages because it is such an important problem, okay? And my recommendation is you once do the curve fitting problem and maybe another one, everything yourself, and then you know how those methods work in principles. And once you master that, you are free to use any of the pre-packaged optimizers in any kind of programming language. But all of those will rely essentially on the same principles, and all of those, for example, will require some sort of initial guess. If they don't, you should worry about how those functions actually operate in their insides. Okay, good. And this brings me close to the end. I'll close with the inversion of our geoelectrical survey. So here's this image again that we are already familiar with. So the magenta line here is a idealized subsurface model that we just assumed. A given set of model parameters consisting of thickness and resistivities of the layers in the subsurface. If I have this, or I assume this magenta line, I can simulate the observations. This is useful for survey planning and so on. But the much more important step is that once I have observations from a different site, how do I find the subsurface model that goes along with this? Okay, and this I do now with a nonlinear least square optimization technique, for example, with the Gauss-Newton method. And so now I went back, I added a little bit of noise to those synthetic observations in this example, okay? I applied the inversion, and this is the result. So the yellow curve is the least square estimate, meaning this is hopefully the best model parameter set that describes the observations. And I can use the yellow line as my model forward parameters or the magenta one. Both of them are actually in this plot here on the left. You can barely see it because they're very similar. And this already teaches you, okay, the magenta line is the ideal solution. The yellow line is the reconstructed. They don't perfectly match. They don't match for a number of reasons. One of them, I added some noise to the data. Second one could be maybe I didn't use the best initial guess, so I should probably revisit this and try the solutions or the robustness of the solutions with respect to initial guesses and so on. However, first I should appreciate all this magic and all those mathematical equations that we have just derived are very general. They will give me the best power law fit to the Rockfall dataset. They will give me the best subsurface model for the geoelectrical survey, and this also applies for many other models which you will encounter in your studies. Okay, so let's summarize. In all nonlinear least squares optimization method, you need a good initial guess. You need to know something about the derivatives, and this is often the key, but for now you can just remember you can do it numerically. All linear problems may have, they don't have to have, but may have several solutions, okay? If your problem is underdetermined, this method may fail and you need to apply other methods. So a problem that's underdetermined means you have more model parameters than observations, so those problems require regularization, which I will treat in another other video. And last but not least, we haven't quantified any uncertainties of our inferred model parameters. And clearly, there will be uncertainties because we have uncertainty in the data, we have uncertainty in the model, and we should somehow propagate this to our model parameters. So we should know how good is our inference. And this is an important step that is not necessarily inherent in this Gauss-Newton scheme. There are other methods which do this more rigorously. However, you can also do that, and I will teach you this in a different video. But for now, you just appreciate that you learned something about the nonlinear least squares optimization methods. I hope you realize that this is an important thing for many, many different type of applications. And you should have the skills to code this in any kind of computer program. And we will do this, obviously, in the exercises. So thanks for listening, and I'll see you in the next video. Bye-bye.